Hello everyone, how are you? How's everything? I hope everything is going well with you and you're having fun with your families and you're looking forward to the end of the semester, which is going to happen in a week. So, in the past few sessions, we talked a lot about the transistors and you started to learn about the BJTs, which were bipolar junction transistors. Today, I'm going to tell you about a new type of transistor, which is called MOSFET. MOSFET FET means field effect transistors. And today I'm going to explain to you why would we call it field effect transistor and what is the difference between this one and the BJT. But what is MOS? Because you have heard about MOS or CMOS technology. MOS means metal oxide semiconductors. So when we say MOSFET is metal oxide semiconductor field effect transistor. Now we're gonna learn what is this transistor. So first I'm gonna start by giving you a general structure of this transistor, but to give you some confidence and comfort about this, I'm gonna tell you this is even simpler than BJT, because you remember the BJT in the beginning it might have been a challenge because it was a new component that you were getting familiar with, but you realize that it's actually not a very complicated thing to deal with. The same thing here. The MOSFET is a very advanced technology. It was a revolution in the field of microelectronics, but as far as we're concerned, it's actually not very hard to deal with it in terms of problem solving and analyzing. So let's see, what is this MOSFET? I look at this picture over here. MOSFET also has 3 pins. Over there in BJT, you used to have a collector, base, and emitter. In MOSFET, you have a drain, gate, and a source. In the circuit level, we show it like this. Look, it's very much similar to the BJT, but in the BJT, these 2 lines were like diagonal, but now they are just straight lines. So the look is very similar. And here you see a little gap between the gate and this other vertical line. So this is how we show this component in our circuits. In this structure, as you see, we have 2 n-type silicon, or n-type semiconductors, which are sitting in a big p-type bar or wafer. You see this whole block is a p-type substrate. In the middle of that, we have implanted 2 small regions of n-type semiconductor. Then, of course, to have a pin, we have to connect a metal terminal. We connected the metal terminal here, a metal terminal here, but for this piece, between the metal terminal and this p-type substrate, there is an insulator which is made of SiO2, the silicon oxide, dioxide of silicon. This is a very good insulator that we have actually applied on top of this wafer, and then we have connected the metal terminal here, which is going to be the gate. Okay, now if we apply a voltage at the drain, okay, we can see here that this is not gonna go through this p-type body to reach to the source. So if you wanna remember the BJT, in BJT your current was starting to flow from the collector and going all the way through the emitter. Here your counterpart for collector is drain, your counterpart for emitter is the source, and your counterpart for the base here is called the gate. So in general, there is no way that any voltage here could turn into a current that is going through this big p-type semiconductor if there is no voltage at the gate. But if we apply a voltage on the gate, think about it, what will happen? Here is a metal, but here there is a semiconductor. There is an insulator underneath, there is a semiconductor. So this voltage will create a kind of a field, okay? So what will happen? This voltage is gonna push away the holes from this region underneath the gate, right? So the holes are gonna go away. So when the holes go away, what will stay? Electrons, right? So when the P goes away, N will stay. So it will create a very small N-type region right underneath this metal oxide piece, okay? Right here. So look, here is the case that we have applied some voltage at the gate. So it pushed some holes away, so it created a small channel. So it's called the induced N-type channel within this whole big P-type block. So now we had an N-type piece of semiconductor in the drain. We had an N-type semiconductor in the source. Now we have a channel, N-type channel. So now we can actually start to conduct, right? Now the electrons can move through this channel from the drain to the source. So the current will start to flow through this channel. So this is the whole story about the concept and about the operation of a MOSFET. So what was a key point here? The key point here was to have some voltage at the gate. We show it as a VGS because we're imagining that S is grounded. We say if VGS is positive, so a voltage is applied at the gate, so there is a potential difference between the gate and the source. This voltage will create a channel for the movement of the electron. So this is the nano concept of this MOSFET, because all of these things are in very microscopic scale. Now we want to see what do we need to know to analyze a circuit including a MOSFET. So what we learned so far was that VGS is very important to make this thing work, but this VGS has to be small, has to be bigger than a certain threshold to open this channel up. That threshold, we call it VT. So we have VTN and VTP depending on an NMOS or PMOS transistor. So whenever this VGS is bigger than a certain level VT, which is VTN or VTP, is going to be given to us as one of the characteristics of the transistor. So whenever this value is bigger than that, we're going to have a channel. Then the VDS, the bigger the VDS, the higher the current that is flowing. So VGS is going to be a must just to open the channel, then VDS is gonna, the higher the VDS is gonna increase the value of the current. As I said in the middle of the discussion, we have two types of MOSFET. We have NMOS, that remember something to remember the right symbol. NMOS is like NPN. This arrow is at the bottom. PMOS is like PMP. The arrow is on the top. And the source follows the arrow. You remember in the BJT, the emitter was following the arrow, right? In the NPN, emitter was down and PNP emitter was up. Here in the P-type, source is up. In the N-type, source is down. This is just for you to remember that you can distinguish the type of the MOSFET by looking at it. Okay? Then our goal in solving any MOSFET problem, in analyzing any circuit including MOSFETs, is to find the current. We call it ID. Like in BJT, we used to find the current IC. Here we have to find the current ID. So over there, what was given to us? Over there, they were giving us the VCC. We know that there is a VBE here, and we had the beta, and we were finding this. Over here, we should know the VDS, the drain source voltage. We should know the VGS, the gate source voltage, if you remember the structure, to make sure that we do have a channel. And what we need to find is to find ID. Very much like the BJT, here we also have three different modes. We have cutoff, we have active, and we have saturation. So now, very simply, I'm going to tell you how to distinguish between cutoff, saturation, and the active mode. Look, this is super simple. What determines the mode here is the value of VGS. It's not as hard as BJT, because in BJT you assume that everything is inactive, then you will analyze it. If you are finding a contradiction, you're saying, okay, so it must be saturation. But here, no. Right away, by looking at it, you can tell. If your VGS is smaller than a certain threshold that I told you, that threshold is the value that you need to open up the channel. So if the VGS is smaller than that threshold, of course it's in cutoff. It's like it's not on, there is no channel to pass the current. But if the VGS was bigger than VTN, then we're also in active or saturation. The active mode, they also call it the triode region. Okay, so triode and active is the counterpart for active in BJT. So if VGS was bigger, it's either in triode or saturation. How do we know? We check VDS after that. If VGS was bigger than this value VTN, so we check VDS. If VDS was smaller than VGS minus VTN, then we are in triode. If VDS was bigger than VGS minus VTN, we are in the saturation. As simple as that. And these regulations was for NMOS. For PMOS, it's the other way around. First of all, if VGS is bigger than VTP, we're in cutoff. So VGS has to be smaller than VTP. You can imagine, right? You needed a kind of like a negative voltage. Then, if VDS was bigger than VGS minus VTP, we are in triad. And if VDS was smaller than VGS minus VTP, we are in saturation. What is VTP, VTN? This threshold. VTN will be the voltage of threshold for NMOS. VTP is the voltage of threshold for PMOS. So these must be given as one of the characteristics of the transistor that you're dealing with. Okay? So now, next step, when you checked the VDS and you figured that you are in triad region, the ID, the current and the drain is found this way. K prime of N, which is, imagine it's a constant, it must be given to you, okay? K prime of N. W over L. W is the width, L is the length, okay? These two are also unique for any transistor. So for any transistor, we have a certain width and a certain length for the semiconductor. So width over length times VGS minus VTN times VDS minus half of VDS square. Look, the formula in the first glimpse might look a bit complicated, but it's actually no big deal. Look, this must be given to you. This must be given to you. Everything must be given to you. Like basically you just need to plug and play. Sometimes they might give you ID as well, but they ask you to find, for example, the width, or they ask you to find the L. So basically you will have one equation and one unknown, not two unknowns. So you will have everything but one of the parameters here, and you will solve it. So when do you use this equation? When you are in the triad region. But if you figured by this condition that you're in the saturation region, you use this equation. ID will be equal to 1 over 2 Kn prime of N W over L VGS minus VTN square. This formula is slightly simpler than this one. But again, it's not a big deal. You just punch in the calculator, you have everything. Just plug and play. In the PMOS, the formulas are slightly different. In the triad region, where this condition was met, your ID will be K prime of P W over L VGS minus VTP times VDS minus 1 over TVDS square. If VDS was smaller than VGS minus VTP, which we were in saturation, then your ID will be simply half of K prime of P W over L VGS minus VTP square. Again, all of these parameters must be given to you, or there will be a way to find them in your circuit. So it's actually, in my opinion, it's way simpler to deal with MOSFET and with BJT, because here you have all the parameters and you just plug and play. You don't even need to do the KVL that you used to do over there. Over there you need to do a couple of KVLs to find the answer here. No, here's direct. You just check the condition, determine the region of the operation, and use the respective formula for the current in that region. One quick thing that I want to tell you is that you have heard about CMOS sometimes, right? CMOS is called the complementary MOS. So it's basically complementary metal oxide semiconductor. So the main basically difference between CMOS and the MOS, basically complementary one, and the normal one, is that this technology permits the fabrication of both NMOS and PMOS transistor on the same chip. Simple as that. So there is a picture here. If you check your lecture note 24 that I posted on Moodle, can actually see this picture that actually both of these NMOS and PMOS are created in one substrate, but we use this metal oxide, the SiO2 dioxide of silicon, as isolation, because I told you it's a great insulator. So we use a big piece of Si2 to isolate the NMOS and the PMOS that can both actually both be created in one slab or one wafer. So I would invite you to look at the slides on the lecture notes number 24, and also to make sure that you will review this video a couple of times to see the whole point about the MOSFET. And as I told you, as you saw, it's not a big deal. It's a pretty simple structure, and you will see how easy is it to deal with this component in the circuits. Thank you very much. I wish you a beautiful day. Take care and have fun. See you. Bye.